Roberto? Yes, please. Try. I mean, present your screen.
So keep on allowing.
Okay.
Is it jump?
Not now. Yes. Yeah, now I can see your screen, but I mean, just show your slides.
Just send transfer screen.
Okay.
For the timing, 2:40.
Show your slides.
See it now?
Yes. Now? Yeah, fine.
Yeah, it's fine. Good.
Okay.
Is Pompa here?
I'm here.
She was there.
Okay.
Yeah, I am here. Can you hear me?
Yes.
Yeah, we can hear you. Yes, thank you.
Azizur Rahman appears twice now.
So Ajijur, could you please log in from only one device, please?
He has left. He has left.
So that, okay.
Yeah. Osmita Dasgupta appears twice. Osmita Dasgupta, please log in from one device.
Yeah. Hello.
Tell you when to start.
Yeah, I mean first the
Can
introduction.
you hear
will-
me?
After that, you will
Yeah,
start.
some introduction. Yeah. So welcome you all, participants, and good morning to you all. So we are going to start our fifth lecture in this series today. And as usual, those who are for the first time in this webinar, to them just one reminder that please do not turn off your microphone as well as your camera so that it actually distracts the mind of the speakers. So it's just a request, and also you may find that there is one button called present now. So please intentionally or unintentionally don't touch that button, because if you touch that button then your screen will start presenting, and that will remove the speaker. And the admin has the capability to remove any participant if he can see like this. So please, it's a humble request to all of you to please be there, and I'm sure that you are going to have nice lecture on symmetries in action. Now may I request our energetic faculty member, Dr. Pompa Pal, to introduce our today's again energetic and very young faculty member. Thank you. Please, Pompa.
Good morning, everyone. Today is the fifth talk in this webinar series. So today's speaker is Dr. Prabrat Das. He did his BSc at St. Xavier's College, MSc at Ramakrishna Mission Vidya Mandir. He did his PhD at Indian Statistical Institute, Kolkata. His research area is geometric group theory. He is young and energetic faculty member at our department. He is a good teacher as well as a good speaker. Today he will talk about symmetries in action. Now I hand over the rest to the speaker. Thank you.
Thank you, Pampadi. Thank you, Shidra, for the introduction. I hope everyone can see my screen, right?
Yes. Yes.
Is the screen visible?
Yes.
So we go symmetry. We have heard, we all have heard about symmetry. Yes, we all have, and also are possibly not two words very closely related in our own understanding. Either are, but see them as two things being very closely related. I will start with a set of pictures. As all of you can see that here there are 15 pictures, various different types. A cobweb, see a is in the beehive, and butterflies, vessels, wings, and so on. Now, in these pictures, striker that are in all this. In pictures, if we notice closely, there are various different types of symmetry. Like if I start with this picture of butterfly, you can see my cursor moving. This is the most symmetry here about this line, right? But also, this is another symmetry here. If we take a reflection about this line, the two states are almost the same. In what sense? If I reflect about a mirror here, the reflection would not seem to be different. There will be differences, but the symmetry, the most happens in that if I let the object undergo transformation, then the object does not change. And what's that anything in this object change? It has a whole does not change.
Just
That yes.
Shubhroto, yeah, could you please check your mic? Your sound is little bit distorted.
Is it? I'm keeping my laptop as close as possible.
Okay, now it's fine, but sometimes it's distorted. Yeah.
Here, can you hear well now? Can you hear me?
Yeah, now it's fine.
Now?
Yeah, but now it's fine.
Let me know when it is closed. Okay, thank you.
Yeah.
Symmetry, we all have standing in all these pictures, like this picture of pentagon. We can see that very evidently there is a rotational symmetry, that if I structure, not any rotation, say about this point, not any rotation would give me the object back. Like these vertices 2, 3, 4, 5. So now if I want to give it a rotation, suppose say 30 degrees, I won't get this object back. But if I give this a rotation by an angle 2 pi by 5, this vertex goes to that vertex, say anti-clockwise. So it goes to that vertex, and all the other such vertices to their adjacent points on the left wise. So give it a rotation by 30 degrees. The object is not that 30 degree. So likewise, you see this picture I guess it's me, but I heard about it. It doesn't matter. Very symmetric object. So you can see, can view this object, this building from top. The today, every will come back as though if we number them, though if we mark the details with different color or number, etc., we will see that it is undergoing some change, actual change. And the object, it would seem that it is suggestion that looks good
Shubhabrata, your
would
voice is
give.
not audible. It's breaking.
I holding the computer and the mic as close as possible. So
Can you just disconnect the mic once more and then
the
again
head,
insert it? Yeah.
Please check the headphone
is
access.
it any? Uh,
Are you using headphone?
Yes, yes, yes. He is.
Also check the please.
is it a headphone? Right.
Hello.
Hello? We can't hear anything.
Shubhabrata, are you there?
I think Shubhabrata has left the meeting.
Yeah, we are trying to connect him. So please
Okay.
wait. We are trying
Okay.
to
Okay.
connect him.
Okay.
So in between, all the participants are requested to write their name as well as the institute's name. So at the end, we'll again provide a attendance form. So in case you miss that form, that will be helpful for you all. So thank you very much.
Hello, am I on?
Yeah, we can see you, but your screen is, I mean, breaking also.
So both of that, can you please remove your headphone? Maybe the problem solved. Maybe it may happen.
Okay, I removed the headphone. Is it any better? Can you hear me better?
It is for better.
Hello.
Yeah,
Yes,
yeah.
This is better.
yeah,
I
it
will
is
switch
better.
off the video then.
Yes, yeah, you switched off the video and
Share the screen. Yeah, it's better.
Okay.
So please
now
present your screen, then simultaneously how it look like.
I have presented screen. Is it
Yeah,
coming?
it's it's coming.
Can you see the screen now?
Yeah, we can see it. Yeah, the
yes,
sound is
Now it is,
better.
yeah,
yeah, voice
now
is
the
also
sound is
better.
very clear. Yeah.
Sorry, the interruption. So we shall continue from there.
Yeah, yeah,
Now
sure.
you can see in all these
Yes.
there are various rural and these are pretty ubiquitous in nature. In all these are all historical objects. Can you see different civilizations? Some old civilizational. From there, we can see that symmetry is quite a part of our understanding of nature. So, if we are to capture symmetry in any formal way, especially mathematical way, then the first place we have to start with is a set and transformations on the set. So what we will work with is a set X, which will be the basic object, and on that we will be adding various different structures. So depending on different contexts. So like the picture of pentagon I had showed there, I can forget whether it's a building. If I am to consider the symmetry of that building, I can totally forget whether it's a building or a picture or something else. I can just take those five vertices and join them with sides of equal length, and, uh, and I can consider that as an object. Now you see, if I consider that object as just 5 points joined by edges, but edges not of same length. the information that the 5 vertices are joined by same length is an additional information, right? If I just consider the set, underlying set, that would possibly be that would consist of 5 elements, 5 points, 1, 2, 3, 4, 5. But the additional information that I have, all the edges joining the adjacent vertices have same length. So that additional information, I called it a structure here, at which to talk about any structure of the system where the underlying object is a set, and on the set we give extra structure, extra information. And a symmetry would be something which would preserve both at the most primary level the set, and at a secondary level the extra information that is given to us. And there can be various secondary, tertiary levels of informations, and depending on, we can ask whether our symmetry preserves all those. Then it would become more and more of a stricter symmetry as we increase the information and expect the symmetry to respect all those informations. So what I mentioned here is that symmetry of a certain structure S is closely related to the idea of a transformation of S, that is the transformation of this total information, the underlying set and the structure. Symmetry is a transformation from X to X, which is a bijection of X as a set, and it respects the additional information. So let us start with the most basic picture of a triangle that we tend to think, the most common one. This is an equilateral triangle with 3 equal sides. A, B, C are the vertices. So if I am to consider a symmetry of this triangle, then and suppose I rotate it about the point D with an angle with again say a 30-degree angle, or say 60-degree angle, then I would probably come somewhere here or somewhere here, get still a triangle, but not this triangle. So I am not sending A to any other vertex. Then A would come somewhere, B would go somewhere, C would go somewhere. It's not a symmetry of the object. So that way we can perform various such transformations on this object ABC, but that's not going to give us the symmetry of it. So we consider only those transformations which takes A, B, C, these 3 vertices to one of these 3 vertices. So the image vertices I call phi A, phi B, phi C, and these phi A, phi B, phi C, they are also one of these 3 points. Now, what's the what's the first transformation? The first transformation is no transformation at all. That is, don't move the object. Even that is a transformation. So in that sense, A goes to A, B goes to B, C goes to C, and the object stays where it is. So what's the next such transformation we can think of, which keeps the object intact? And that is, A kept fixed. A do not go anywhere. A does not go anywhere. B goes to C and C goes to B. That's a reflection about this line joining the centroid to A. In this case, you can call it anything, perpendicular bisector, angle bisector, anything in this case. So this is a symmetry we can very well understand. Keeps the object unchanged. What's the next one? Next one is B kept fixed and C going to A going to C. Fine. Similarly, C kept fixed, A going to B, B going to A, and the other two rotations by angles. One rotation is you send A to B. How much angle do you need for that? You need this much of a rotation, right? And this is 120. So this is 120-degree rotation that is required to send A to B. B will then go to C and C will move to A. And that would keep the triangle intact. And that transformation is A going to B, B going to C, C going to A. And you can do that one more time, and if you do that, then A will come first to B by 120 degree, and then again another 120 degree would take it to C. And then into A, and A to B. These transformations. So we can see that this object, this equilateral triangle, which has a lot of symmetries, a lot in the sense that it has 6 such symmetries. Okay. Now, why did I say the word lot? It will be clear from the next two pictures. Now, let's look at this picture of an isosceles triangle. And here too we have this transformation where A goes to A, B goes to B, C goes to C, the identity transformation, which does not move the object. And this transformation, this is the only other symmetry, the only other transformation that keeps the object intact. That is evident from the picture, that this is the only other symmetry this object has. You cannot reflect about this line here and get the same object back, or this line here and get the same object back. So, and what is the restriction? Who posed that restriction? Now, if you remember the word I said, the notation I have given, x comma s, and I said that s is the extra information, and if I want to find the symmetries, it has to first be a bijection of the underlying set, in this case the set ABC. But we have seen in the previous picture that ABC had these six bijections, and this is the complete list. So ABC, the set consisting ABC, has these 6 bijections. But for this object, not all of them work. Not all those objects, all those transformations, bijections, are giving me a symmetry for this object. And what's the restriction? The restriction is that this information, this extra information is given. And that information is the two sides have same length. If I rotate, then this edge comes here, this side comes here. And I know that these two sides do not have same length. So that transformation is not allowed. So that's not a permissible symmetry here, even though that is a symmetry of the underlying set. It is not a symmetry of this object. This object, an isosceles triangle. If we go to the next picture, sorry, change, just a minute. Yeah, back. So, if we go to the next picture, it's of a scalene triangle. Here too, I have A, B, C, the underlying set. But you see, neither the angles, neither any two angles or any two sides are of same gradient, same angle or same length. So, apparently in this triangle, we do not have any symmetry, which is very, very evident that none of these 3 sides are equal, none of the angles are equal, so there is possibly no symmetry, and that's it. Even though this object has the same underlying set, and that underlying set can have at most 6 symmetries, none of the non-identity symmetries of the underlying set is a symmetry of this object because of the restriction of side lengths. So let's look at the set of symmetries of 3-element set, the set we were considering all this time. We had a notation ABC. Here I write it 1, 2, 3, and writing it this way, it seems familiar. I guess all of you who are listening this have seen a symmetry group. Group of symmetries of n letters. So here I have chosen 3, and this is the class. This is the set of all bijections called permutations of the set 1, 2, 3. This is the identity one. These two are the two rotations. In fact, here these are the order 2 or order 2 permutations. Here you see, like the previous one in the equilateral triangle case, here this element is fixed and this 2 has a transposition. 2 goes to 3, 3 goes to 2. So this is a cycle in the sense, if you operate this element twice, you get back this element. All these elements, all these 3 elements, if you apply them twice, you get this element back. Now you look at this element. Here you have, by applying I mean composition. Since I am talking about bijections, this is a notation I have given. It's a very standard notation for a bijection of this kind of a set. Here it means phi is the map which sends 1 to phi 1, 2 to phi 2, 3 to phi 3. And this phi 1, phi 2, 3, phi 2, phi 3 are again elements of the same set. Here we could have chosen a bigger set. This notation still remains the same. Here you see these two transformations, which takes 1 to 2, 2 to 3, 3 to 1. We have seen this transformation in the equilateral triangle case. There, what did this transformation represent? It represented a rotation by an angle 120 degree. And we can see that gives us, if I apply this transformation 3 times, not 2 times like these transformations. If I apply this transformation back to back 3 times, I will come here. Why? Because first time 1 will go to 2, and in the next time 2 will go to 3, and then in the next time 3 will go to 1. So 1 will go to 2, 2 will go to 3, 3 will go to 1, and then I am back to my position. And not only 1 comes back, 2 also comes back to 2, because 2 goes to 2, 2 goes to 3, 3 goes to 1, and 1 goes to 2. So 2 comes back to 2 after application of 3, after 3 times application of this transformation phi 2. Similarly for phi 3. So these are all very familiar things, I think, for all of you, and I will spend less time on this now. So I call this collection, this set of objects of all these transformations, I call it by this, I denote it by this notation Sx. This is also pretty standard. And we can see that this collection is closed under composition. These are all bijections, that means mappings of this set, and collection of all these bijections, this collection is closed under composition. Take any 2, compose in any order you like, you will still get an element in this collection. And as their composition of mappings, it's associative. I hope all of you know the associative notion. And we have special elements. And you see, for this element phi 1, if you compose it with phi from left and right, you still get phi back. And for each element here, you can easily see that you have, for each phi, you have an element I denote, it's a standard notation again, phi inverse, which when composed gives me the special element back. So they are inverses. Here you see for phi 4 the inverse element would be phi 4 itself, because it has order 2. Why? Because 1 is already at 1 doesn't move under repeated application of phi 4. 2 goes to 3 and 3 goes to 2. So if I apply it one more time, 2 goes to 2 and 3 goes to 3, so I get identity. So this is also very clear that they have all these properties. And now these properties remind us that it's the defining properties for a group, for an algebraic structure called a group. And that is the main focus of this today's talk, today's seminar, that symmetries of various objects, what are they? Are they something esoteric? No. For a mathematician, group is a very real object, and the elements of groups, we just see them. We tend to look at them because of because how we were introduced to them. That we have a set with a binary operation and a few properties, and that makes the set with that binary operation to be a group. I find that definition, and many others find that definition, it's just a definition, but it is not revealing what the group is, what it is good for. It is good for understanding symmetries of certain object. That is the purpose of studying groups. And we can see here, if we consider the set of symmetries of just a simple set 1, 2, 3, that gives us a group. And which group is this? This is our familiar S3, the permutation group on 3 letters. So we see that any collection of any bijections of any given set by the same argument gives us a group. And essentially, groups will act. And that's what we want to look at. Fine. So it is clear from the above discussion that symmetries of a set, they are symmetries of any set X. They are the same as elements in the set of so-called permutations, the set we just have seen, and in general it's denoted as X. So a group G acting on a set X, we have heard of this term group action. So here in the title I mentioned that groups act, and that's it, because groups are meant to act. Groups are not objects which is set with a binary operation which follows certain properties. That's such a plastic definition. Groups are meant to act. Act in what sense? Just the way we have seen these transformations acting. Just the way we have seen these people, these objects acting. They were transforming, they were rotating A, they were rotating this triangle, they were transforming A to B, B to C, C to A. So that's the action they do. That's the job, that's the role of the symmetry. So in that sense, for us, from now on, a group will be something which just acts. And in a moment it will be even more clear that why a group is necessarily supposed to act, because by the very way it is defined. So a group acting on a set X means any element, take an element G, that can be realized as an element sigma G. sigma g here is a symmetry. So now we do not have any extra structure that we mentioned by S. We do not have any such things. We just have a set X. We have a group G, and we say that the group G is acting on the set X. What do I mean by that? I mean that any element from the group can be represented or can be realized as a permutation or as a symmetry of the set X. This is what I meant by that. So this is a symmetry, this is a bijection of a set, and at the set level, bijections are the only symmetries, you don't have any other structure. So sigma G is such a map from X to X, it's a bijection, and a group acting on X, it means that a group element G would behave like this. And by that I mean that there would be a map which sends a group element small g to an element sigma g, which actually does the job. It apparently, it looks like G is doing the job. It is, but in the guise of sigma G. Actual job is being done by sigma G. That's the transformation. Fine. So in most books you will find it is introduced this way, that group action is something like a map from G cross. If G acts on a set X, that means you have a map from G cross X to X, which sends a pair G comma X to G dot X, some other point in X. I wrote the same thing, but just the other way. After this, you would find that if I fix the first coordinate of this map, G, and vary the second coordinate, I get a map which sends small x to G dot X. And that gives a map from X to X, right? So I just wrote that map before writing this, because it seemed to me that this comes first. G acts on X means it can be realized as a permutation of X. Anyway, this is nothing new, and by all this information, by all this thing, we mean a group G is acting on a set X. Okay, so I will take some questions maybe at 12:30. So if you have some questions, please write it down, or ask me at 12:30. I will pause for 5 minutes then and take questions. So now, given that we have all these, we can define these objects. This is an orbit of an element X. X is here. And orbit, I couldn't draw the picture here. You all have seen orbits of planets, planetary motion, right? And there you have some sort of a dynamical system, some movement is going on, right? Some motion is there. Planets are moving in some orbit. I'm not going into the fact why the planets are moving and so on, but there is something which is making these people move. Now, the moment there is a movement, you see there is a trajectory, the way the trajectory it follows to move. And there in the planetary motion, it's sort of a continuous situation. There, if you start from one point, then that moves in a continuous fashion. Its trajectory would look continuous. It may not be so. If we have a group, say we have seen examples of discrete groups, finite groups, for them trajectory would be, orbit would be discrete. So here is what I mean by an orbit. And this is a stabilizer. Stabilizer of an element X is the collection of those group elements which do not move the point X. And it is very easy to see that stabilizer gives us a group. It's a subgroup of G. You see that if G and H are 2 points which don't move X, then their composition will also not move X. So you can see it's associative as a subset, and it's it's closed under composition, all the group properties. And you see that from the definition of group action, the identity element is not meant to move any point in X. So you have the identity element in this set, and if G is an element which does not move X, G inverse, you just apply G inverse on both sides, you see, then G would cancel, and that would be identity application on X, and on the right hand side you will find G inverse applying on X. So you see that G inverse of X also fixes X. So sorry, G inverse also fixes X. We can define something like something called a quotient. And what is a quotient? You just take the set of orbits. You have a group, you have a set, group acts on the set, each element has orbits. This is also not difficult to see that orbits are, so this group action defines an equivalence relation, and orbits are equivalence classes under that relation for these elements small x. And the equivalence classes, the collection of equivalence classes under that action defined by the action is called a quotient of the space X by the action of the group G. So what is G really doing here? Suppose X is a set, and just a minute, I will try to draw some. So I have a set X. So this is my set X, and I am saying that G is a group which is acting on X. Is the screen visible? Is the screen visible?
Yes,
Yes, yes,
yes.
yes.
So if I take a point here, I call it little x, and suppose G, small g is an element here in capital G, then application of small g, as I have mentioned that small g restricted, small g gives me a map from x to x, and this is a symmetry, right? So if x is a set, then G moves the element small x to G small x, right, to another element. And then if I so what is the orbit? The orbit is you take this x and move it by all possible G. So that would give you a collection of points, right? And that collection also is not a, it has a structure. What is it? This collection of points, you can think in some sense a copy of G, copy of this G sitting inside capital X. It is like G dot X, right? So this is like a copy of G sitting inside X. And what is a quotient? A quotient is, that quotient is a set which is sort of counting how many different such copies of G are sitting inside my capital X. So all these copies of G, as I said that this is an equivalence relation, and an orbit, orbits are the equivalence classes. So we understand they're disjoint, and so if I want to know that how many such copies of G are sitting inside X, and in fact they're tiling X, they are partitioning X, then that answer to that is the quotient space. So I will come back to pictures again. Now let's go back here. So examples. I haven't described very difficult examples mentioned of the job because it's a we so here I have a group of integers z. Can you see the screen? Is it all right?
Yes.
Yes, yes, it is visible.
Your voice is little bit distorted.
So
Yeah.
my voice is distorted again.
Now it's
Yeah, now
fine.
it's fine. Now it's fine.
Uh, I don't know, maybe due to the internet connection. My broadband is not working. This is mobile network. So anyway, I have a group of integers z acting some noise coming from the background. Uh, excuse me.
Supriyo, can you switch off your microphone?
Okay, now it's better. So I have this group of integers z acting on the real line. That's a very standard basic first example. So what is the action? An element from z is like n, an integer. So for that n, just like I have written here, n g goes to sigma g. So similarly, I send n to some symmetry of R1, and that symmetry I have denoted sigma n. What it does is it translates x by n units, and this is a very nice example. You can see that, okay, fine, let us look at the orbit. Suppose I take the point, suppose I take the element, say 0 in the real line. So what would be the orbit? What would be O of 0? Or even 1? What would be O of 1? It would be the entire set of integers sitting inside R1, right? So the orbit of the element 1 is 1 plus g dot x. What is that here? It is 1 plus n for all n coming from the integers. That means the orbit of 1 would contain all 1 plus n's, 1 or plus minus n's for all n in R1, right? So what is that? What is that set? That entire set, if we look at, is z again, right? And or you can see that orbit of any integer would be the set of integers sitting inside R1 again. That should tell you. Let's see this. I mean, what was the equivalence relation? Equivalence relation was two elements are related if they are in the same orbit under the group action. I mean, if there is an element, group element, which takes one element to the other. Suppose I have taken two elements. One is 2, another is 7. Now you can see that there is this element 5 which takes the element 2 to 7, and there is this element minus 5 which takes the element 7 to 2. So you can see if I take the orbit of 2, there will be a 7 in that, and if I take the orbit of 7, there will be a 2 in that. Similarly, you take any two integers, they will be in the same orbit under this action, right? Now, if I take the point half, from R1, what would be the orbit? The orbit would be all the integer translates of half. 3 by 2, 5 by 2, 7 by 2, and so on. And here on the left hand side, minus 3 by 2, minus 5 by 2, minus 7 by 2, and so on. Right? Also minus half in this. So that, if I see, it is like, now if what if I look the orbit of minus half? I would see that the orbit of half and orbit of minus half are the same again. And what describes that? Because the difference between these two elements is an integer. That's why their orbits are same. So I have mentioned here that a quotient is collection of all the orbits. And if I go by that definition, you see that I have written here that R mod Z is S1. People may wonder why I have written S1, which is a notation of circle here, but it can be shown that this cube is actually a circle. And I have a favorite analogy, pictorial analogy for this. What is happening here is like, I think everyone has seen kite. Everyone has in some point the kites, or I don't actually know the English word for the object called latai. Pardon me, those who are not from Bengal listening to this lecture, uh, it's probably something, probably know exactly the word. Any, you imagine that R1 is like an infinite thread, and I have a cylinder, and I have to roll the thread on that cylinder, and I have to put the thread wind around that cylinder. Now you see that if the cross section, if the length of the cross section is say 2 pi, then at each 2 pi length I will come back again to the same point on the cylinder, on the cross section of the cylinder. Mark those points on the thread with some color. At each 2 pi distance I will get the same color. That way, if any point after, suppose I have put the entire thread on this cylinder and marked one point with some color, and then if I open it at all these 2 pi intervals, there would be the same color. If I have marked some different point, it would have come at a different place. But the difference between any two such points would be of same color, would be an integer multiple of 2 pi. So that's pretty nice, and that explains why I'm calling this R mod Z to be S1. And then I can just extend this action. It's just the product action, just for the ease of understanding. Let me again go back to the picture. So suppose I have a real line here. The action of Z was giving me sending a point X to say sigma 1. If I say sigma 1 is a translation by it sends X to X plus 1. So X would be sent to X plus 1. And another point, if I call it Y would be sent at Y plus 1, right? And similarly Y plus N. So I have to see to understand this R mod Z S1. You see that only the points between 0 and 1, they are giving you distinct orbits, distinct equivalence classes. Even the orbits of 0 and 1 are same. Only if you take one, you have to leave the other in the set of orbits. So all the points inside, they are giving you different distinct orbits. And that way, if you take the quotient, that becomes something like you take this interval 0 and 1 and join the two ends to get a circle. That's what I mean by the quotient to be a circle. Now by the product action, what I mean is you have R cross R and you have Z cross Z acting on R cross R. Lagging behind the bit. Okay, so R cross R is something like this. Now, earlier I was acting like I sent this point to that point. That point to, I just moved them along this line to my left and right, right? Now I have a second component, right? So what I do there is I do the same thing along this line. Here I was sending them left and right, here up and down. Now any other point here too can be translated to the right, to the left, to upwards and downwards, right? So any point can be moved up and down, left and right by the action of Z direct some say or Z2 on this R2, right? So the action is the same component wise. Now, how do we get the quotient, the set of orbits R2 mod Z2 to be? I said in case of R1, in case of R1 it was just a minute. So it is S1 cross S1. So why do I say that? You see that if you move now this point by the action of the first Z1 say, which is moving it left and right, then this point goes to the left, and up and down is fine. It's already on the vertical axis. And then this point, if I let the second component of Z act on this, then this point is moved up and down, right? Again, if I take this point moving left and right is already considered, up and down is already considered. Now this point. So this point also can be moved up and down, right and left, right? So I can understand any point, suppose any point I give you here, then by some application of M and N, you can move this point back to some point in this square. Suppose that point is in the square, in this square. Now this coordinate, this has an integral coordinate m comma n. Just by m on this, on the first coordinate, and minus n on the second coordinate, you bring this point back here, right? So that way you can fold the entire plane to a square like this, and you have to look at the orbit, right? You have to look at any two points who are related. And these 2 points are related because by an application of 1 on the second coordinate, you send this point there and that point here by a minus 1, right? So even these 2 points are related. These 2 points are related too. Here is a square whose points at the same height on the boundary are also related. So what I do from this is I identify this point with that point, this point with that point. So what I get is a cylinder. I get a cylinder. I think that's clear to all of you. and from this I get a cylinder, and here I get a circle. How did I get the circle? I got the circle just the way I got R mod Z is S1, giving me the circle. Now on this, there is one circle here, one circle there. But on these two circles also, you have points who are equivalent. They differ by 1. So they are also supposed to be identified. And what you get identifying them, you get something like this. And this is the S1 cross S1, which is a torus. If anyone has seen these objects, this is a torus. Okay, so going back to the slides, just want to mention quickly Cayley's theorem. Since we are talking about symmetries, symmetries, the first symmetries we come across are the symmetric group, the set of permutations. And Cayley's theorem tells us that a group can be seen as a subgroup in some permutation. That's what Cayley's theorem tells us. Okay, so it's already 12:30 now. Maybe before going into Cayley's theorem, I can just take 2-3 questions. Is that
If
possible?
you have any question, you can either type it in the comment box or you can ask. But one by
How long
one.
can we continue, Shuman? 1 o'clock.
1 o'clock, yeah.
1 o'clock. Okay. So maybe I will take at most 2 questions.
So
So that's
if
for
you
now.
want to ask any question, you can switch on your microphone and ask. Okay, someone is asking, please explain the concept of S1 once more.
S1 cross 1. Sorry, S1 cross
No,
S1.
S1 once more. S1 again. I mean, they are actually asking why R by Z is S1.
So why R by Z is S1? Oh, okay.
Yeah.
So R by Z is S1 you can prove directly, but here I just gave a pictorial argument that what is S1? S1 is a circle, right? S1 is a circle, right? So you can think of it this way. You take a map from R1. R1 is a group. You take a map from R1 to S1. S1 is also a group, right? S1 is a group under multiplication. You think of S1 as a subset of the complex plane, and there you can multiply e to the I theta, e to the I alpha, and so on, right? Multiplication there, e to the I theta, e to the I alpha is e to the I theta plus alpha, right? So now, if you take the map where you send a real number from the real line, take x and then send it to e to the I pi x, then what will be? So this will be a homomorphism, right? And now this will be a surjective homomorphism, just the way I was saying that you wind a circle, you wind a thread around the cylinder. So the same map I am talking about here. So this would be a surjective homomorphism, and you just try to find out what the kernel of that map is. You will see the kernel. Sorry.
It's okay, you carry on.
You would see that the kernel of that map would turn out exactly to be Z, and you can then apply the first isomorphism theorem. You have a surjective homomorphism, you have a kernel, and then you take a quotient by the kernel, and then the quotient group is isomorphic to S1. That way you can convince yourself. Okay. Even otherwise, if you look at R1 as a topological space and Z is just a group, I haven't mentioned that yet. It will come in a moment in the next slide. So if you look at R1 as a topological space and Z as a group acting on a topological space, even then the quotient would be a topological space which is S1. So that's why I gave that example. It explains many different facets in one small thing. Anyway, so I think I answered your question. Any other question? Or shall I carry on?
Someone is asking to show you the previous slide,
What slide?
the slide earlier than this.
Oh, okay, this one?
I think so.
Ah. Okay, so what about it?
I mean, I don't know. I mean, they're asking.
Okay.
And someone is asking, what is the object of group? I don't know what is the exact meaning of this question.
Okay, maybe I will take these questions after I finish.
Okay. So I think you can start again.
Okay. Thank you. So let's look at the finite case for Cayley's theorem, and the infinite case is nothing different. It's essentially the same. Just see that you have a group. Now consider the group as a set. So you can multiply a group element with another group element. Right? So have a finite group G, you list them in this fashion, G1, G2, Gn, and then you multiply them with a fixed group element. Now you see that since you have finitely many elements, and you are sending G1 to GG1, G2 to GG2, Gn to GGn, so this collection is also same as this. So these elements are also these elements only written in a different order maybe. And that order is given by this. So these numbers are just giving a different order, a different permutation of these numbers 1 to n, right? Nothing different. Since these elements are just these elements written in a different order maybe, so that translates to a permutation. All what is written here effectively is 1 going to sigma hat G1, 2 going to sigma hat G2, and so on. So essentially, whatever this thing is doing, this sigma G is doing by sending G1 to GG1, G2 to GG2, is captured by this permutation. 1 going to sigma G1, 2 going to sigma G2, and so on. Right? So that's why I have written that this entire thing gives rise to this permutation sigma hat G, which is an element of Sn. Why? Because it's a permutation of 1 to n. It's just a permutation of the indices. Right? So if you take this map from G to Sn, given this way, you can show that this map has trivial kernel, and then you can take the image of this map, and the group is isomorphic to the image, and in that case the group is isomorphic to a subgroup of a permutation. Essentially same proof works for the general case as well. What we get from this is that a group can be seen, an arbitrary finite group can be seen as a subgroup inside a permutation group. Permutation groups are very particular groups, very precise groups of certain type, and they have precise properties where you can explicitly write down elements in a permutation group. They break up in a certain way, they have certain very nice properties. So you can avail all those properties for your group by seeing the group inside a permutation group. That's what the Cayley's theorem does. So now from that point of view, a question can be, if I have some other group which has better properties and I can embed, I can see my group inside that group with better properties, then will I be able to understand the group better? Yes, that is true. It's essentially the motivation behind presenting a group inside a linear group. Looking at representations of a group inside linear groups. Now, what are linear groups? Linear groups are symmetries of vector spaces. Now, vector spaces we understand is a structure where we can. It's an additive group structure where we have an additional scalar multiplication with field elements and so on. And there is a set of axioms to define a vector space. I am not going into that. What I want to mention here is, like we are looking at symmetries of objects. What did I mention in the beginning? That a symmetry preserves the structure. It's kind of the best map which preserves the structure in the sense that for the underlying set, it is a bijection, which is the best map possible for the underlying set. And on top of that, what it is doing is it's preserving the structure, right? In this case of a vector space, a symmetry from that point of view is a map which is a linear isomorphism of the vector space, which preserves the vector space structure and by linearity, and is an isomorphism. It's also bijection. Okay, so those are symmetries of a vector space, and the collection of all such symmetries is called the general linear group. In case of Rn, if you take V to be Rn, we can think of it. I mean, not only for Rn, for any finite dimensional vector space, you can think of this group as n by n matrices, group of n by n invertible matrices. Okay, so now if you have a group which acts on a vector space, then what will it do? G cross x, we had a map from G cross x to x, and that gave us a map sigma G, which is a map from x to x. Here it should give us a map from V to V, right? So a group element small g should be assigned to an element in GLV, right? That's the way we had seen earlier inside the permutation. So here is this. Here is how we generally represent a group inside a linear group, and this is the definition. I have not given any specific example for that. Why I mentioned this is that symmetries will change. Earlier I said in the beginning that symmetries will change depending on the context. If I have a set, just a set, no further structure, something which I call a symmetry can no longer, may no longer remain a symmetry if I put additional structures to it, right? Something which preserves the topological structure may not preserve the linear structure. Something which preserves the differentiable structure may not preserve the topological structure. Something which preserves the topological structure may not preserve the differentiable structure, and so on. So here I am talking about linear symmetries, symmetries of a vector space, and if a group acts on a vector space linearly, this is how we can see a group inside the group of invertible n by n matrices. And that gives us an enormous advantage because linear groups have many good properties, and this way you can see your group G, which is acting on a linear space inside GLV or any other subgroup for that matter. That gives us a great deal of advantage. Here one thing is, if V in addition has an inner product structure and G acts on V where it respects the inner product, I mean the form associated to that. That means it preserves the norm also. So here these type of matrices would be the orthogonal matrices. Say if you have GLNR, this would be the group ONR. So for V to be Rn, the group of general linear transformations, I mean invertible linear transformations or isomorphisms is GLNR. and the orthogonal ones are O and R. These are the familiar groups. Anyway, so now similarly for a topological space, the symmetries are homeomorphisms, which are the bijections at the set level again and respect the topological structure. So time and again we are finding that symmetries are giving us as a group, which is the group here, symmetries of a topological space. So they are here, and now if a group G, some arbitrary group G, acts on a topological space continuously via, that means via homeomorphisms, then I get a representation of G inside the home, and that kind of gives me a handle, a way to see the group element G as a homeomorphism, because it was acting via homeomorphism, right? So symmetries of a topological space, they form a group, and if a group G acts on a topological space, I can see that group sitting inside the group of homeomorphism. So typically homeomorphisms are very large groups. So many times people look at discrete subgroups of such groups. They give a great deal of information as well. So discrete subgroup, I mean the orbits are discrete for all elements. Now for an example of an action which is continuous via homeomorphism, I just mentioned this example earlier. This example works as well here. So you see this map is a homeomorphism of R2, right? You can just write down this map, draw pictures, you can get a better understanding that these maps are homeomorphisms. And that's how Z2, the group G, is acting on the topological space. Here the topological space is R2. As I just mentioned some time back, that Z acting on R1 as a topological space, you can also think of a topological quotient, quotient by 2 patch. So here too you can check that these maps are homeomorphisms, the group Z2 is acting, but also it's a discrete action in the sense that you take any element xy, look at its orbits, x plus n, y plus n, but you see that in a neighborhood, half neighborhood of any of the translates, you won't find the second translate. Within half neighborhood of one translate of xy, you will not be able to find any other translate. That means it's discrete. So these are very important actions. Now, so I've written that I am repetitive here, but that is precisely the point, because symmetries are ubiquitous, and depending on the how rigid or flexible your structure is, I mean, like you can remember the example of a scaling triangle. It was too rigid to have any symmetry because the metric informations on the sides were too rigid, right? You did not have any symmetry. On the other hand, if you had a equilateral triangle, so everything is nice, you can see that it is a symmetric object, very symmetric. However, I mean, whichever angle you look at it, it looks the same. So that's the symmetry of it. So for metric spaces, symmetries are better thing to look at, and they are the isometries which preserve the distance, the distance which comes with the metric here. So here the symmetries are those bijections which self maps which preserve the distance, and they also you can see that they also form a group, and similarly you can represent the group which is acting isometrically on some metric space. You can represent the group inside the group of isomorphisms the same way we had discussed all this time. Here, earlier this map was a homeomorphism. In case of vector space, this map was a linear isomorphism. Here, this map is an isometry. The context change the contexts change and the maps also change accordingly. But you see, the same example works here as well. This map, this action is an isometric action. R2 is a metric space also with the Euclidean metric, and you can see that the same map, the same action is an isometric action as well. Okay, so in the end I will talk briefly about free groups. We generally don't get to see these groups much in the usual course, usual bachelor's and master's course much. So these groups are, in a sense, group theoretically. People may say that they are not so interesting because you don't have a relator. These are free groups. That means no word in this group you have. I mean, only the identity is a trivial word. Any other word you consider in this group is not trivial. So that is a very strange situation we come across here. But these are very universal objects in some sense. Why? Any group G is a quotient of a free group, right? I think you have seen this statement at least about a free group. So this is not difficult to see as well. So you can check that yourself. So for a group G, you can find the free group. In fact, you just take the generating set of the group G and consider the free group, which I haven't defined yet. You just consider the free group on that generating set of the group G, and then you have a map from the free group on generating set S to the group G, and you can show that this map is a homomorphism, surjective homomorphism. Just look at the kernel, and the kernel is called the set of relators. Those are the words which are killed, which are trivial in the quotient. I mean, in the group G. So we have something called a presentation of the group G, which is I forgot to mention the S here. The group G is isomorphic to Fs quotiented by a normal subgroup. The normal subgroup, the generating set of the normal subgroup is R, is called the set of relators. So it is like F of S, F over S divided by normal subgroup generated by R. If this is the case, G is denoted by S, comma R. I mean, S is the generating set, R is the set of relators. That kind of describes the group as a whole. So we can very quickly construct construct a free group. Just take a set S, and what you do is just form all sorts of words. I mean, I have taken here the set S1, S2, Sn. You take, I mean, if this is the alphabet, and you can concatenate as many alphabets as you wish, finite. So, and then take the word like S1 to the power N1, S2 to the power N2, S1 to the power minus N3, and so on. So you just take S1, S2, Sn, raise them to any integer power and club them together. That is a word. Now there is something called a reduced word. When you have a word, subword like Si followed by Si inverse, you just delete that subword. So you keep doing such things. What you end up having is called a reduced word, and in that word you don't have any S inverse type of subwords. So now you take all such collection of all such formal reduced words in the alphabet S, and then what you have on that set, if you define the multiplication of two such words, just by juxtaposition, you see that after juxtaposition, the object is still a word, and if it is not, it may not be reduced, but if it is not reduced, just reduce it, and that is again inside your fs. So it defines your multiplication. It's a closure property like. An identity element is an empty word. You just take a word and multiply, juxtapose an empty word to the right or left, doesn't matter, you get the same word back. It may seem to you nonsense, but that's how it is. And then inverse of a word is just the word written in the opposite order with changed indices with changed signs. That's the inverse. And the associativity is obvious. Just change the bracket, position of the bracket, that's all. So that's all. That says that this is a group. This collection of reduced words on the alphabet S forms a group. And now the cardinality of the set S is called the rank, and this is not so difficult, that if you generate free groups over two sets, X, S and T of same cardinality, the groups are isomorphic. And for that very reason, if the cardinality of the generating set S is n, since it does not depend on the generating set, it just depends on the cardinality. This previous statements vouches that. So we can write Fs just by Fn, and for n greater than 1, Fn is not abelian. For n equal to 1, Fn is just a group of integers. But n 1 onwards, I mean 2 onwards, is not an abelian group. So these are the free groups. They are very nice objects, and geometrically speaking, they are kind of the best possible objects. So now I want to mention something, a very nice object, very nice result. I know I'm almost out of my time, but I have only one more slide after this, which is not so important. This slide is a little important. It's very easy to understand. You will understand in a minute. It's called ping pong lemma. I have 1 or 2 more minutes. Anshuman or Shukla?
Yes.
So this is called ping pong lemma, and this ping pong lemma is a very nice result. It's a very small result, but it's very useful. Its applications are again ubiquitous in something called geometric group theory. So what it says is, suppose you have a group G, which is generated by 2 elements A and B, okay, and the group G is acting on a set X, okay. Now if you have 2 disjoint non-empty sets inside X, one is XA, another is XB, such that any power of A takes XB inside XA, and any power of B takes XA inside XB. Okay? Any power, any non-zero power of A will take XB inside XA, and any power of B will take XA inside XB. Then G is isomorphic to a free group of rank 2. I mean, this is probably the most surprising thing one would expect out after this result, but that's the case. See, I've just written down the proof briefly. If G is not isomorphic to a free group, just by the previous description here, I said that any G is isomorphic to a quotient of a free group, right? So if the group itself is not free, then there has to be a proper quotient, right? And that means that there will be some non-trivial word here, right? such that G is quotiented by, I mean, a free group is quotiented by some non-trivial normal subgroup to give you G, right? Here the claim is G is isomorphic to a free group. That means no such normal subgroup generated by relators in the denominator that you have seen appears here. That's what we have to prove. So suppose that it is not true, then G has to have, if it is not true, then G has to have a non-trivial relator R, right? Fine. And what is a relator? Relator is a word in the generating set, right? So what is the generating set here? A and B. So the relator would be a word in A and B. Now it is easy to see that an element of G is conjugate, any element is conjugate to an element of this form. Now this may seem surprising, but it is not. You take any element you like, arbitrary element, some powers of B, some powers of A, some powers of B. If you think that I will take some element which does not start and end with an element, an A or a power of A, then if it's even better, you just take a conjugate with some power of A. So what I claimed here is any element is conjugate to an element of this form. So if suppose you take one side it's B, another side it's A, fine, then on that side where it is A, suppose it starts with some power of B and ends with some negative power of A, say A to the minus 2, okay, then I can take, I can conjugate it with, say, if it ends with A to the minus 2, then I can conjugate it with, say, A cube. So I conjugate it with A cube and then it starts and ends with powers of A, right? So it's not very difficult, right? That any element is conjugated to some element of this form. Now, you see, no element of this form is an identity. Why? Because an identity, if you have observed the definition of a group action carefully, identity is the element which fixes everything, right? Now, an element of this order cannot fix anything. I mean, cannot fix everything. Why? Because if you take a point in, say, xb, then just do this ping pong. You have some powers of A, just keep on applying the powers of A, powers of B, powers of A, powers of B, and so on. Okay? And then you will see if you have taken an element here, a point here, that ends up here. If you have taken an element, similarly you can change the argument a bit and the terminal and the initial elements, and you can similarly argue with XA. So what is the upshot? Upshot is, even you don't need to do that. The upshot is that there are elements in X which are not fixed by G. Now if G has to be a relator, an identity element in capital G, then it must fix all elements small x. Now it does not. So that means G is not trivial, right? Now you have no trivial element in G. What is that? That has to be a free group. So that is ping pong lemma. It is. It may seem very fancy. Of no use, but you believe me that this is possibly the most useful thing in many parts of mathematics. It was used significantly in Mosto-Rigidity theorem. It was significantly used in many aspects of Riemannian geometry. This is a very important result, but it's so simple. And it's just using the symmetry of a set X, which is a group G, which is generated by two elements. Satisfying simple facts like this. It's a very nice result. And I will just quickly mention these things that a group can be seen as a graph, which is called a Kelly graph, where the vertices are the group elements and the edges are like you join two vertices by an edge if it differs by a generating element. So if S is a generating element and if you have one group element G, then you join an edge between G and GS, something like that. So that is why I have written that edge set is G cross S. So that's the graph. That's how you describe the graph. And it does depend on the generating set S, but not one would see not too much. I mean it does depend, but the dependence is not too much in order to do geometry. I mean, if you consider doing geometry, large scale geometry. And then this graph itself can be thought of as a metric space by assigning each edge to have length 1. Define each edge to have length 1 and then take any path in the graph. That path will have a length. Now joining any two vertices, it's a connected graph. So now joining any two vertices, you take all possible paths. Now you have lengths for all of them. Take the infimum. So that gives you a metric on this graph. I have written with a slight abuse of notation. It's not exactly the word metric, but this is quasi-isometric to the word metric. That's why I called it the word metric. Word metric is actually defined in terms of the words I talked about in the previous slide. Anyway, and when one group has two generating sets, finite, then the graphs you get out of this way are not exactly isometric, but they are almost like isometric, called quasi-isometric. And G itself acts on that graph by isometries. The left multiplication by group elements, just like the Cayley's theorem you observe, G, G1, G, G2, etc. So that action here on the graph, the vertices of the graphs are group elements, so you can move them. Also edges move to edges, and that gives you an action on the graph. So that action is actually an isometry under this metric. So this interplay is very, very important, and it reveals a lot of information about the group. So roughly that is all I wanted to say. I just wanted to make you think that groups are objects which make things move. They act on spaces with different structures, and then they can be thought of or looked at as symmetries of those structures. That's all. Thank you.
Thank you, Shubhaprabhu. And it's a nice lecture starting from few examples from real life to ping pong lemma. So it's really great. And now it's the time for question answer session. Before that, I'm just going to share you the link for this today's attendance. So the link will be valid for 4 to 5 minutes. So please do it quickly. And also type your questions to the chat box so that one by one that can be answered.
Stop the presentation?
No, please don't stop it. I mean,
because the question answer session will be there.
There are many questions regarding the ping pong lemma. So the first one is to show that slide once more.
And the attendance is at 1:08 p.m. So that link is at 1:08. So please fill up this form first and then ask the questions or whatever, because the link will be gone after 5 minutes.
Okay, the first question regarding this that I can find here is that can we analyze this for any n?
Yes. I mean, do you mean that any number of generators?
Well, I will ask one who has asked this question, I would ask her to switch on the microphone and ask it herself.
I would say that this can be generalized, this lemma can be generalized for more generators, finite number of generators.
Okay. some are asking about the applications of ping pong lemma, where it can be used.
Yeah, it can be used to show. See, there are something called many different analytical and geometric properties. One of them is called amenability, and a group is not amenable if it has a free subgroup. Okay, so if the group has a free subgroup, then it is somewhat large. I mean, if you can show that your group has a free subgroup of rank 2, you say, because all other free subgroups, free groups you can consider inside that would not be amenable. And you can use the ping pong lemma to show in many situations, you can show existence of free groups inside your group, inside a group. Just find a situation where your group, you can let your group act on some set like X, find some two disjoint subsets XA and XB, find some two elements, and find some two disjoint sets like that which behave this way. And then you know by this lemma you have a free subgroup. It is very simple.
Okay, another question is that can it be is it having any application in dynamical systems to show that the system is chaotic?
I do not know a chaotic system, but I guess it may have. I frankly do not know.
Someone is asking what is the stabilizer of a group.
Stabilizer of a group, I didn't mention a stabilizer of a group. I said when a group G is acting, when a group G is acting on a space X, here you see, the group G is acting on a space X, then a stabilizer of an element. You see here, it's an element, and I am looking at the stabilizer element, stabilizer subgroup of that element, which is the collection of group elements G, which fixes that element. The name itself suggests that it should stabilize X.
Okay. Another thing is regarding free groups. What is a free group? Some are asking.
What is a free group?
Yeah.
I just mentioned slide.
Just on that slide.
Yeah. I briefly talked about the construction of a free group, and the free group is one. Any group is a quotient of a free group. In that sense, it's kind of the parent group. So you take any group, look at its generating set, generate a free group the way I described here, and get the group as a quotient of that group. So in that sense, any group comes from a free group.
Okay, another common question that I can find is that can you suggest any book to study geometric group theory?
Yes, I can. There is a introductory text now available from Springer. I don't know whether Indian editions are available or not, but it's called Geometric Group Theory, and its author's name is Clara Lowe.
Can you just type that in the?
Yeah, I will write it. Yes. Any other question?
Yeah, one question is can you explain the Cayley graph of a group?
Cayley graph of a group.
Yeah.
Okay, so I gave the definition. I did not have time and I did not give a picture of a Cayley graph. Just look at this graph. So look at this group Z. and look at the daily graph would look like this for the generating set 1. Suppose I generate it with 1, okay, the daily graph would look like this. It would go on this way and this way. So this is the 0, 1, 2, minus 1, minus 2 and so on. Now you see that what did I say, that between a vertex G and another vertex which looks like GS, you have an edge. Here you see what is GS, what is S? S is the generating element. There you have only one generating element. And you see that 0 and 1 they differ by 1, 1 and 2 differ by 1, 0 and minus 1 differ by 1. So you do not have any edge by 0 and 2, right? You do not have any edge between minus 1 and 1. So that's how you draw the graph. Similarly, you can try drawing the graph for z square.
হ্যালো স্যার,
Yes.
হ্যাঁ বলছিলাম, আপনি দেখুন প্রথমে ডায়াড্রাল গ্রুপ দিয়ে আমি যদি কনসেন্ট্রেট করি, তাহলে ডায়াড্রাল গ্রুপে দুটো পথ, একটা রিফ্লেকশন আর একটা হচ্ছে রোটেশন। সমস্ত রোটেশনে একটা সাইক্লিক গ্রুপ, আর রিফ্লেকশনের প্রতিটা অর্ডার 2। এবার আমি যদি যে সাইক্লিক গ্রুপটা একটা এলিমেন্ট দিয়ে জেনারেট হবে সেইটাকে নিই, আর একটা যে কোনো রিফ্লেকশন নিই, তাহলে হোল গ্রুপটাকে আমি জেনারেট করতে পারবো, রাইট? এবার আমি বলছি এটা একটা সিমেট্রিক গ্রুপের ক্ষেত্রে সম্ভব না। যে কোনো ফাইনাইট গ্রুপের ক্ষেত্রে আমি তার একটা প্রপার সাবসেট নিয়ে পরে হোল গ্রুপটাকে জেনারেট করতে পারি।
বুঝলাম না আরেকবার।
হ্যাঁ, আমি কি সমস্ত ফাইনাইট গ্রুপের ক্ষেত্রে আমি তার প্রপার একটা সাবসেট নিয়ে পরে হোল গ্রুপটাকে কি জেনারেট করতে পারবো সবসময়?
যদি পুরো গ্রুপটা নিয়ে নিই তাহলে তার সাবসেট
সাবসেট স্যার,
প্রপার সাবসেট।
হ্যাঁ,
ফাইনাইট গ্রুপের জন্য।
হ্যাঁ, যে কোনো ফাইনাইট গ্রুপে।
I think it should be yes.
তুমি ইনভার্ট গুলো বাদ দিয়ে দাও,
হ্যাঁ
ভালোই হবে।
প্রপার সাবজেক্ট হয়ে গেল।
আইডেন্টিটিটা বাদ দিয়ে দাও।
আইডেন্টিটিটাকে ঢুকিয়ে রেখে লাভ নেই কিছু। আইডেন্টিটিটা তো একটা এলিমেন্ট
না।
ওকে, তাকে কি আমি জেনারেটরের মধ্যে ঢুকিয়ে রাখবো? লাভ নেই তো কিছু।
এবার তো আপনি বললেন ইনভার্টগুলো বাদ দিয়ে দিতে, তাই তো?
রিডান্ডেন্ট এলিমেন্টস থেকে বাদ দিয়ে দেবো।
আচ্ছা, এবার ইনভার্টগুলো ছাড়া যে এলিমেন্টগুলো পড়লো সেটার একটা যদি সেট ফর্ম করায়, তার সাবসেট দিয়ে আমি করতে পারবো?
তোমার কোয়েশ্চেনের আনসার হয়েছে আগের কোয়েশ্চেনের?
হ্যাঁ হ্যাঁ হয়েছে।
আচ্ছা, এরপরের কোয়েশ্চেনটা কি?
না, আমি যে ইনভার্টগুলো বাদ দিয়ে দিলাম তারপর তো একটা সেট পড়ে রইলো, এটা দিয়ে আমি এখন জেনারেট করতাম।
বলা যাবে না ওভাবে। এটা তো তোমাকে গ্রুপের ডেসক্রিপশন দেওয়া থাকলে, গ্রুপের প্রেজেন্টেশন দেওয়া থাকলে দেন ইউ ক্যান টেস্ট, তাই না? And I mean, one group can have many generating sets, whose maximal element is the group itself, right? Na? So you are possibly looking for efficient generating set. That is not always, readily answerable. কোনটা সবচেয়ে efficient? You take the relation দিয়ে কোনটাকে avoid করা যায়, কোনটা না নিলেও চলে।
Hello, Shubhabrata da, this is Shantan. Can you go to the slide of ping pong lemma?
Just a minute. Yes.
Yes, that condition. See, a to the k xb subset xa. Is there any analogy of that statement with orbit stabilizer language in orbit stabilizer language? Can I reformulate the statement AKXB subset XA in orbit stabilizer language?
Orbit stabilizer theorem is a counting statement. Okay.
No, I am not asking. No. See, I am asking, can we reformulate this statement in terms of orbit and stabilizer language? That was next.
What I do not understand the question. I mean, what do you mean by reformulating it in orbit stabilizer language?
See, I am having a feeling. I mean, I don't know. I'm having a feeling that this condition, whatever you have written, AK, XP, subset XA, is there any connection with the orbit space of? I mean, because your
where you generally, I'm telling you, where you generally use this lemma is. I'm giving a concrete example. Suppose you take a group which is sort of isometric group of a negatively curved, simply connected, complete Riemannian manifold. ঠিক আছে?
Okay.
সিমেট্রিক স্পেস টাইপের জিনিস সেখানে তার বাউন্ডারি বলে কিছু জিনিস হয়, বাউন্ডারি অ্যাট ইনফিনিটি।
ওকে।
এবার ওই গ্রুপগুলো সেই বাউন্ডারির উপরেও অ্যাকশন থাকে। ওই বাউন্ডারির ওপরে তুমি যদি এরকম সুন্দর সাবসেট খুঁজে বের করতে পারো যারা ডিসজয়েন্ট এবং যাদের মধ্যে একটা পিং পং হচ্ছে, দেন ইউ find a free subgroup of the group of isometry or the group you are looking at.
Okay.
ঠিক আছে? এবার ওই বাউন্ডারি অ্যাকশনের উপর মানে জেনারেলি আমি তোমাকে যতটুকু বলতে পারি সেটা হচ্ছে যে এই যে এ আর বি এলিমেন্টগুলো নিয়েছি এখানে, এই এ আর বি এলিমেন্টগুলো জেনারেলি দে আর hyperbolic elements. I cannot elaborate here, but they are generally chosen to be some hyperbolic elements. মানে কি তাদের অ্যাকশন থাকে এরকম হাইপারবলিক স্পেসের উপরে এবং তাদের ফিক্সড পয়েন্ট কিছু থাকে। হাইপারবলিক এলিমেন্টের বাউন্ডারিতে দুটো ফিক্সড পয়েন্ট থাকে। and these are kind of such elements A and B, এবং যখন তাদের অ্যাক্সিস গুলো ক্রস করে তখন তারা ওরকম ফ্রি সাবগ্রুপ জেনারেট করতে পারে। ইভেন ইফ দে আর কাইন্ড অফ রিলেটেড অর অ্যাসিম্পটটিক তখন তারা করে না, এরকম একটা সিচুয়েশন ভাবতে পারে।
ওই যে সাবসেটটা ওটা কি তাহলে ওই অ্যাক্সিস ক্রস করার মানে কন্ডিশন মানে ওটার সাথে কি
না তুমি দেখো ওখানে এই এলিমেন্টটা ওই পয়েন্ট দুটোকে ফিক্স করছে। এবার তোমার এখানে এমন একটা জিনিস চাই যেটা দুটো সেট খুঁজে বের করতে হবে ওর মধ্যে। মানে আমি যে বইটার নাম লিখে দিয়েছি ওটা আরো একটা বই আছে অফিসার্স উইথ জিওমেট্রিক গ্রুপ থিওরিজ, ওখানে বেশ কিছু সুন্দর ছবি আছে কি করে এই সেটগুলো তৈরি করা যায় বাউন্ডারি। আমি জাস্ট একটা এক্সাম্পল বলছি কুইকলি, মেবি আদার্স আর ওয়েটিং। Just take a free group.
এটা offline নিয়ে নাও because there are many others who are waiting. So network issue is there for many persons.
Yeah. One line, take a photograph of a free group on two generators, disconnect it at any vertex, and then you will get at least 4 disconnected components. Then you can do a ping pong. That's all.
Okay. Thank you.
Any
other questions you can just ask? Anyone?
Here also some questions also there. Symmetry has effect on modules.
Symmetry has effect on
modules.
Of course. You look at the HOM. তাই না? ভেক্টর স্পেসের ক্ষেত্রে তুমি যেমন জিএল দেখছো ওখানে তো HOM দেখছো, মানে ওটা এন্ডোমরফিজম যখন মানে আইসোমরফিজম দেখছো না, আইসোমরফিজম তো ওখানেও হয় তাই না?
So another question, Manavendra Giri, what kind of objects are words?
What kind of objects are
words?
Words. ওয়ার্ড বলতে আমরা এখানে একটা অ্যালফাবেট ধরে নিচ্ছি, জেনারেটিং সেটটাকে অ্যালফাবেট বলছি। আর ওয়ার্ড হচ্ছে ওই অ্যালফাবেট থেকে ধরুন আমরা লিখছি যে অ্যালফাবেট ALPH বি, এই যে লিখলাম এই জিনিসটা তো ওই ALPH এগুলো দিয়ে লিখলাম। এবার এখানে যদি আমার এখানে চান্স নেই, in the English language I cannot take a square, L cubed or p to the minus 5, but here I can take s1 to the power k, s2 to the power l and so on. এবার পর লিখে দিলে যা দাঁড়াবে সেটাই একটা ওয়ার্ড।
Next, the same, he also asked the same question, similar question. Is it some special set or is it tuple?
Sorry, কোনটা স্পেশাল সেট?
This odds actually.
No, it's not a special set. Just you construct it. You take a set which you call the alphabet, and from that alphabet you call something which you call word. Word is just like a monomial. মানে আমার এই জেনারেটিং এলিমেন্ট গুলোকে একটা monomial লিখলে যেমন দেখাবে সেরকম, ঠিক আছে?
So another question by Rakib Mondal.
অ্যালাউ করছে, মানে মাইনাস জিনিসগুলো অ্যালাউ করছে। হ্যাঁ, একবার বলুন।
No, another question by Rakib Mondal. He asks, would you please give some examples of symmetry in real life or in nature?
I have given it in the first slide.
Yes, you also provided. And another question, sir, give some application of symmetry in real life or how symmetry acts in real life. I thought Professor Dash, Dr. Dash already gave the answer in the
I can. Those are some symmetries we can see around, but there are practical uses also. Like I don't. I think today group theory is used very much by chemists and people who design drugs. And there they look at the groups and their actions, the molecular structure of the drugs they design and how they work, that depend a lot on the symmetry of that structure. And so they use group theory and group actions there to study such things.
So, one more question by Sunil Kumar Pandit. He asks, do an action and its Euler-Lagrangian equations have the same symmetry?